chemical, it basically allows us to name it. Okay, we subclassify organic compounds based on their functional groups. And the reason we do that is because it gives them specific chemical reactivity. Okay, so we end up having specific chemical reactivity. It also defines their physical properties, because heteroatoms, as you learned in general chemistry, introduce dipoles. If you have a heteroatom, which is electrical, and invariably they're electronegative, and so they suck electrons and they create a charge disparity within the molecule, which creates reactive sites, which we'll get into a little bit later. Here's an example of that. Here we have a carbon atom, just a general diagram here of a carbon atom joined to a heteroatom, in this case an oxygen. It could equally be a nitrogen or a halogen atom. And the heteroatom is electronegative, so it draws electron density towards itself. But the consequence of that is that if it draws electron density towards itself within this bond, it creates an electron deficiency in the other atom that makes up that bond. Does that make sense? So we end up with what we call a nucleophilic site and an electrophilic site, something that likes nucleophiles and something that likes electrophiles, and that gives it chemical reactivity. However, there are molecules, it's organic chemistry, and organic chemistry is a little bit misleading. It originally comes from its original designation, where it was believed that all organic material was obtained, could only be made from living sources, until the mid-1800s, when Friedrich Wöhler created urea, which was then only known to be made by mammals, created urea out of inorganic salts. Okay, so the name organic chemistry is a bit of a misnomer. Some leading organic chemists prefer to call it carbogenic chemistry. It's the chemistry of carbon. So we know that carbon is the central atom in this subject, and many of the carbon molecules don't have heteroatoms in parts of the molecule. But what they do have is they have pi bonds, and that's the next site of reactivity. So whenever you have a pi bond, as well as a heteroatom, you have a site of reactivity. And we discussed in the last chapter, the two electrons in that pi bond can act as a nucleophile, they can act as a base or a nucleophile. So the molecule doesn't have to have heteroatoms, but as long as it's got pi bonds, we can have reactivity. There's a lot going on in these initial chapters 1, 2, and 3, because a lot of it involves catch-up. And some of it involves just little things like this that you need to know about. So in organic chemistry, the molecules are usually large. I could draw another example, I guess. So you can have really large molecules in organic chemistry. For example, like that. I'll add something else to it, why not? I'll put maybe an OH here. Okay, you don't need to worry about that, what that looks like, that molecule. You don't have to worry about what it looks like just yet. But the thing is, there's a lot going on in that molecule, right? And let's say I wanted to just highlight a particular reaction of a particular functional group in that molecule. All I have to do is basically rewrite the rest of the molecule as the symbol R. Here, what you have to remember is that wherever you designate it as R, the atom underlying it, that's part of the rest of the molecule, has to be a carbon. So I'm going to show you this now. I can redraw this molecule and I'll draw it in the same orientation. And if I want to just highlight this OH group here and show you how it reacts in that molecule without having to draw all this all over again, does that make sense? This R group here represents all of this for convenience, And the R group starts on a carbon, and that's bonded to an OH. Do you see what I did there? Okay, so the R group in organic chemistry is just a very quick way for a chemist to write down a larger part of a molecule on which the functional group that they're looking at or explaining to you is attached. Does that make sense? So it saves me from drawing that all over again each time. Okay? So yeah.
So for that R, do you always assume that it's single bonded all the way around, or like is there another way to write it as a double bond on the other side?
No, it will always be single bonded. So for example, if I wanted, I'll introduce you to these functions. If I wanted to introduce you to, if I wanted to express the reaction of this functional group here, I know the colors I'm using are not, don't seem to be showing up very well on the screen. If that one is bonded to 2 carbons at each side. You see that?
Yes, sir.
And they're different. One's got a double bond, so I could, if I draw it in the same orientation, which I normally wouldn't, I would normally kind of redraw it, I could call this R, and I could call this R, and because one's different, I would call this R1, and this R2. Does that make sense?
Yes, sir.
There's a single bond coming from an R. So you go as far back as you need. So I had to go back. I wanted to show this carbon group as the functional group, so I went back to the carbons beyond that. Does that make sense? Yeah. Okay. Excellent. Very good. Now, let's look at the first set of functional groups that you have to kind of know things up. And those have no heteroatoms whatsoever. They only have carbon and hydrogen, the principal elements in organic chemistry. Now, we'll get into how to name these as the course progresses. But the first one is called an alkane. And I want you to notice that it's signs, so every little detail actually has a significance. In this case, as we progress, only one letter is changing, but the molecule itself has a completely different functional group. Do you see that?
Yes.
Okay. Now the first one, which is an alkane, it's made up of just carbons and hydrogens that are all sp3 hybridized. So if I was to draw that first one out, it would look like this. And in general, alkanes are unreactive. We can make them react, but the reason why we can make them react, but there's a very, very limited set of reactions, like 2 or 3. But essentially, we regard alkanes as being non-functional. Does that make sense? There are no pi bonds, like I mentioned, and there are no heteroatoms. So that is not classified as a functional group, but you need to know it in comparison. Then we start to lose hydrogens. So we lose these 2 hydrogens and fold these 2 bonds in like the 2 doors of a double door and form a pi bond. We get this molecule here. Now we do have a pi bond, and it's a reactive site, just like I mentioned to you. So this double bond, carbon-carbon double bond, is regarded as a functional group. And we can lose a further 2 hydrogens, and they can close in and form another pi bond in the bottom here. So now we have 2 pi bonds, one at the top, one at the bottom. And along with the sigma bond that initially joins the 2 carbons, we have 3 bonds, so we call that a triple bond. And that's the next functional group. Now, all these molecules here, well, all of these are hydrocarbons, first of all. Let me just do that, hydrocarbons. They're all hydrocarbons. Can you see that? So all 4 categories are. The reason they're hydrocarbons is because they contain hydrogen and they contain carbon only. Now we're going to subdivide that. I'm going to go over here, and these are called aliphatic. Hydrocarbons. Okay. So we say this is saturated, and that these are unsaturated. i.e. you've lost hydrogens. Okay. We'll get to that later. So those are all examples of aliphatic, and two of those subcategories are functional groups. Then the last one is special. This is a benzene ring, and a benzene ring if we draw it in a Lewis style, it looks like that. Okay. But just like when we draw any skeletal structure, we don't have to draw the carbons. We can indicate the carbons just by the bend in the chain, and we can still show these double bonds. So that's where the structure of benzene comes from. Now, this designation here, phenyl, if I use my symbol R to represent a molecule, I can indicate the presence of a benzene ring by writing down pH, which stands for phenyl. It's pronounced just like the vegetable that smells of licorice or anise. I don't know if you have it in North Louisiana. I think maybe in Super One or something. So it just sounds like phenyl, okay? And that's specific because there's another compound that we'll encounter later that's spelled similarly, but it's said completely different. It's pronounced completely different. So this phenyl, and a phenyl group is a functional group. And so if I draw it out in full, it looks like this. Okay, I don't like to draw it that way because it looks like a sad face. See that? So I'll just show you my preference. Doesn't matter really. Okay, so that's a phenyl group. And you'll realize when we get to chapter 4 that when we define groups like this with just a couple of letters, it's usually the first two letters of the name defines it. Very good. Okay, so just a reminder, this book uses Z to represent a heteroatom that is electronegative. So whenever you see Z, it's usually pulling electrons towards itself. Okay? And we're going to look at 6 categories of functional group that involve only heteroatoms, like this. And then we'll look at another 6 after this that are specific to carbon-oxygen double bonds. And unfortunately, you've got to commit these to memory. Okay, so practice drawing them. Maybe put them on index cards and then on the other side, give it a name. So this is the general structure we're going to be looking at now, and how we classify them, and how we name them. So let's have a look at the first one. And I may have mentioned this in the first class when we did, well, there's a lot there, so let me just, don't know if you can you see that at the back, or do I have to kind of zoom in a little bit? Zoom in a little bit. I'll draw some of these out again. We don't need the 3D structure there. That's just fancy pants stuff. Let me get on a page.
This chart's in our notes, right?
Sorry?
It's on the slideshow?
Yeah,
Yeah.
it's on the slides. Everything's on the slides.
Cool.
So you have a reference. Okay, so the first category is alkyl halides, and I think I remember in chapter 1 when we did Lewis structures, I may have mentioned, just like we have an R group, the R group I mentioned today that stands for the rest of a larger molecule beginning on carbon. The symbol X is our general symbol in organic chemistry for a halogen, so that could be a chlorine, fluorine, iodine, that kind of thing. And when when you have a halogen attached to a carbon, we call it an alkyl halide. So it's an alkane usually, and the alkane has one of the hydrogens replaced with a halogen atom, fluorine, chlorine, bromine, iodine, and it's called an alkyl halide. There's an example there. It's called methyl bromide or bromomethane. Don't worry about the names just yet. When I draw a structure of an alkyl halide, say this, and I'll make it general still. Okay. I want you to notice that the alkyl halide is attached to this carbon atom. I'll highlight it as a dot. And if I draw in how many H's are on this carbon atom? Let's draw 2. And I'm just going to draw them in just to help others see this. So there's the 2 H's. Now I can refer to R groups. Now that you know what R groups are carbon groups. Okay. And that halogen is attached to a carbon that only has one R group attached to it. Do you see that? Okay, there are 2 H's here and here, but there's only one R group attached to this carbon atom. Okay, and we call that a primary alkyl halide. So it has a subclassification. There are 3 subclassifications. And when we say the word primary, you don't have to write down the word. All you have to do is write down the number 1 with a degree sign on it. And, oops, okay, 1 with a degree sign on it. And you don't say 1 degree halide. This 1 degree sign actually is spoken out loud as primary. Does that make sense? So you write 1 degree halide, but you say primary halide, alkyl halide. Now, I can now do the rest pretty quickly. Now that you know we've got a primary, if I draw this structure, there's another alkyl halide. There's the carbon it's attached to. How many H's are there on that carbon that's not? Only 1. But you'll notice that the carbon on which the halogen is attached, it has 2 R groups. So this is called a secondary alkyl halide. We can keep on doing that. Switch it up a little bit and go on the other side. The carbon which bears the halogen has 3 alkyl groups attached to it. Do you see that? So that, all in logic, is a tertiary, and I'll write that down for you. That's a tertiary alkyl halide. Good, and we'll repeat those subclassifications with other compounds. So let's move on to the next one. The next one is an alcohol. And an alcohol has a hydroxy group attached to it. So there's alcohol. This is called a hydroxy for obvious reasons. Hydrogen and an oxygen. So that's an alcohol, and it has the same subclassifications. So this would be a primary alcohol. So the molecule is called an alcohol. And this would be a secondary. So listen to what I'm saying. The carbon bearing the OH group has 2 R groups attached to it, therefore secondary. And then the last one, tertiary, of course, and there's an example.
So this is going to go for most of them. Most of them are going to have a first, a second, and a
Not all of them, no.
Okay.
Not all of them. So this next, this is a good example. This next one is called an ether.
Okay.
In Victorian times, we used to, ether's got a very pleasant, sweet smell. It's highly flammable, and it's one of the primary reasons why we don't use naked flames in organic chemistry labs. You don't use Bunsen burners, because the whole place would just blow up. Ethers are a particularly good example. But ethers are easy to spot. They have alkoxy groups attached to them. So here we have hydroxy, and I could draw this from either side, but it's got an alkane group and an oxy, so that's called alkoxy. That's the type of group that's on there. And the molecule itself is called an ether. But how do you spot it? Well, you look for an oxygen. It's flanked on either side by a carbon. Doesn't matter what the carbon groups look like, if they're, and they can be the same. That's a symmetrical ether, or they can be different, and that's an unsymmetrical ether. Does that make sense to you? Yeah. And so if you have an oxygen flanked by two carbon groups, it's an ether. This one, though, does have the subclassifications, but you look at it slightly different. With alcohols and alkyl halides, you look at the carbon on which the halogen or the OH group is attached, and then ask yourself how many R groups are attached to that carbon. These types of compounds here, you just look directly at the heteroatom itself. So here we have amines. And amines are nitrogen compounds. The simplest amine is ammonia, which you may find in your kitchen, bathroom. And ammonia, as you may know already, looks like this. And that corresponds to the Lewis structures I showed you at the beginning of the course, and it follows the covalent bonds and lone pairs that I showed you for a nitrogen atom on the second period. It has one lone pair, forms three bonds. If we successively remove those H's and replace them with R groups, we get three subclassifications of amine. So if I add one R group here by replacing this H, that's a primary amine. You see that? Sorry about my one. That's a primary amine. And then if we continue to do that process, R groups, I think it's easy to see. And those can be the same or they can be different. That's now a secondary amine. But this time I want you to just pay attention to the fact that you're actually counting the carbon groups directly attached to the nitrogen this time. Okay. And of course a tertiary amine would have three R groups. Here. Next, thiols. Thiols smell like rotten eggs, or they just smell bad, like skunk spray, rotten eggs. Any of those kinds of nasty smells usually result from thiols.
Is that because of the sulfur?
That's a sulfur.
Is that because of the sulfur?
Yes, absolutely. And smelly compounds usually have low mass. It means they're easily volatilized and they can be smelled readily. Does that make sense? So a lot of them are small molecules. And you'll smell things like byproducts like that. If ever you have patients that have to have like cysteine or any kind of amino acid that contains sulfur, you'll smell from the vial that kind of rotten egg type of smell. So I want to remind you of where sulfur lies. Thanks for asking questions. Sulfur lies directly below oxygen in the periodic table. So we say they're isoelectronic. They have the same kind of electronic structure. So just like oxygen forms two bonds and is two lone pairs, sulfur does too. Okay. And it's in simplicity. You can get more than that, but simplicity. So anything that works for alcohols, so we had alcohols which look like this, we can replace that oxygen with a sulfur and we get thiols. sense, we call them thiols. You see the connection there? Okay. And then the last one, again, is replacing oxygen with a sulfur. So we had ethers before, and ethers involved oxygen. And if we replace it with this isoelectronic counterpart below it in the periodic table, we get what we call sulfides. So thiols and sulfides, we just basically replace the oxygen with sulfur. Yes, is that good? So those are the first 6. You have to remember, and it just basically involves a heteroatom attached to a carbon or 2. You need to know what they're named. And then the next set, I'm going to draw, I'll use the ordering they have in your book. But basically the next 6 have this functional group in common. And the functional group is and I'll just redraw it just to slow me down so I can teach it. It's a carbon doubly bonded to an oxygen. Okay? And of course the carbon can be attached to other things. But strictly speaking, the carbonyl is this group only. The carbon-oxygen double bond is called a carbonyl group or carbonyl group. I've been here so long, when I grew up, my pronunciations sometimes are British, sometimes they're North American. I just don't know which is which. So if I pronounce it in a weird way to you, that's part of my cultural exchange to you. Okay? If I pronounce it correctly, then I'm good. Okay, so that's a carbonyl group. Now, let me do this my way now. Follow the same sequence they have in the book. So I'm going to take time and draw. I'm going to draw 6 carbonyls to show you how easy this is to remember. So they all have this in common. They all have carbonyls. I'll draw another. Here's the next thing. That makes it easy because they all have that in common, so you know how to draw that. The next thing they all have in common is on one side, either left or the right, because we've got a double bond here, so we've got 2 single bonds to go. They all have a carbon group. They're all attached to a larger molecule on which this is the functional group. So the reason I present it this way to show you how easy it is to memorize. There's only one thing you've got to memorize, and that's what's bonded to the other side. Now just recognized, I put all those carbon groups which represent the rest of the molecule on the left. I could easily have put them on the right. Does that make sense? What I want to stress to you is that they all have that in common, and the only thing you have to remember is what I'm going to put down next, and the name that's given to it. Okay. So, if the other side just has an H, it's called an aldehyde. And just to let you know, I'm not a complete jerk. I do feel guilty of it not zooming. It's just that I was very cranky, and I'll correct it next class, but I've done it, so. So aldehyde has an H on one side, and then if we add another R group to the other side, instead of an H, it's given another name. It's called a ketone. Okay, aldehydes and ketones. When something is if you speak to people in the fragrance industry or people in the wine tasting industry or any kind of liquor tasting, whatever, anything that smells herbaceous or grassy is referred to as aldehydic, because all those components that make it smell like herbaceous or grassy freshly cut grass. It's a lot of aldehyde components. And then you're going to ask a question now, just stretch. Okay, and then we've got ketones. And then the next one has an OH on it that has a hydroxyl. Now, this is a tricky one. So we can draw the OH out in full, or if I just draw this up here, several forms, I can condense. I'll give you the name in a second. Often we condense that OH bond and just write OH. Does that look okay? Or we can take it and we can condense the whole thing and we can write down COOH, representing those in it. Or we can bring those O's together and write CO2H. So those are all valid forms of that.
Oh.
Yeah? And that's called a carboxylic acid. Very good. So this is a hydroxyl, and this is a carbonyl, and together we can call that functional group a carboxyl for short. So that comes from carbonyl, and that comes from hydroxy or hydroxyl. Okay, it's a combination of two. What do you call it when you combine two words together to form a new word? Do you remember? It's called a portmanteau.
Yeah, I wouldn't have got that.
You wanna go? I just like to. It's okay. I'm just asking. You can just combine the two things together. Okay. Next, after carboxylic acid, we can replace this H in the carboxylic acid with a carbon group. So if we do that, we can write out this. Now again, we normally just condense this bond and we write it like this. You see that? Or we can condense it even further, just like I showed you before, and write CO2R. Just like we did up here. Okay. So all those, and that's called, its full name is a carboxylic acid ester, because it's derived from a carbon. We just call it an ester, so don't worry about what I just said there. Why did you say it then? Because I just want to give you the complete picture. So that's an ester. And esters are sweet smelling. Actually, incidentally, carboxylic acids smell, the small molecules smell of like rancid cheese, smelly feet, or rancid butter, all those kinds of nice compounds that you get.
Do ketones have a signature smell?
Hmm?
Do ketones have a signature smell?
Ketones, they don't have really a specific smell. Like, I guess you know the smell of, this is a good point here. Like, I'm just going to tell you about the smell, and remind me if I forget, because I digress off. Okay, so I have allergies, and for the longest time, the only thing that works for me is something called brompheniramine, and it's a molecule, it's an antihistamine, but it's got a bromine atom in it, and hence the name brompheniramine. But the one that's sold over the counter, you can get in all pharmacies, I can't remember the trade name of it, but it's called chlorpheniramine, and it's the same molecule but with just a chlorine atom. But the one with the chlorine doesn't work for me, but the one for the bromine does. And that's physical properties of molecules, including medicines. They change just by changing the atom size or just by changing a small group. It's phenomenal, those changes. And in fact, you probably were told in general chemistry, the difference between gold, which is inert and doesn't react and is a precious metal and solid, and mercury, which is toxic, liquid, and a completely different color, is just one electron. Okay, were you told that? Yeah? Because it just changes the size. Okay? And the same happens, ketones are the same. So one of the simplest ketones is acetone. and it's got an acrid smell. The girls that have smelt it with toenail polish or fingernail polish, whatever remover, it has acetone in it as well as other things, and it gives an acrid smell. You add one more carbon, and you get butanone, and butanone just smells like butter. Just one carbon difference. That's pretty amazing. Okay, so that's why I didn't specify that. I deliberately ignored that, but I see you caught on to that. Okay, so this one here, the next one, if we add a nitrogen group to it, so nitrogen makes 3 bonds, one of them is bonded to the carbonyl, that's called an amide. And that has a subclassification. The others do not, but this does. Because we can replace these hydrogens here with other R groups. So this one as it stands, when it just has the carbonyl on it, this nitrogen, the carbonyl carbon gives it one R group. So that's called a primary amide. So you could write down this for that one, primary amide. But you should also know that you get a secondary and a tertiary amide. And you get those by replacing those H's. Does that make sense? So the tertiary amide would have 2 R groups here. This one, which is the R group of the carbonyl, and then 2 others here instead of H's. Does that make sense? Okay, that would be the tertiary amide. And then the last one is an acid chloride, which is the most reactive of all of them. And you'll see that later. So this is an acid chloride. Its full name is a carboxylic acid chloride, just like carboxylic acid ester. I don't think books explain that anymore. So that's an acid chloride. Okay, there's an E there. The upshot of all this is that eventually you're going to have to predict reaction outcomes for molecules later on, and through experience and covering reactions you'll see which ones are more reactive than others. But before doing that, you've got to understand the language of organic chemistry. If I gave you an exam next week on this chapter, but the questions were all in Mandarin, I'm just assuming nobody speaks Mandarin here. There's no way you could even begin to tackle the problem because you can't even understand the question. So you have to become familiar with the language of organic chemistry, and that's why we give you all these names. And you should be able to they give you some examples in your book. You should be able to just look at a molecule and tell me what functional groups are present. So here, an OH attached to a carbon is an alcohol, but what subclassification of alcohol do we have here? Which one is it? It is secondary because the carbon that bears the OH has 2 R groups on it, therefore it's secondary. Do you see what I did there? And this is an ether. It's an oxygen flanked by 2 carbon groups. We have an aromatic ring, benzene ring. Here we have an amide. What type of amide is that? Primary? Yeah, correct. And then here we have an amine. By the way, I always, when I look at a molecule, the first thing I look for is a carbonyl. And that reduces it just to 6, and then you can just look at what's either side. There's an R group and there's an N group, so it's an amide. Here we have a nitrogen, and there are no carbonyls next to it, just R groups. And this is a secondary amide. Do you see that? We just look at the groups directly attached to the nitrogen. So your book problems will give you some examples of those. And let me just show you one more. Here's a tertiary amine. The nitrogen has 3 R groups attached to it. We could also classify this aromatic ring as a phenyl. Do you see that? And this is a ketone. It's a carbonyl flanked by 2 carbon groups. Pretty much it. So it allows us to name compounds, but it also affects physical properties as well as chemical properties that we'll get into later with reactions. And I just want to remind you of the main types of intermolecular forces.
Oh, yeah.
Yeah, do you remember that?
I do.
Yeah. Now, all the compounds we've been drawing so far, they have covalent bonds, but you should also remember that you can have ionic bonds. And we're not going to look too much into ionic bonds, but they're between basically a positively charged cation and a negatively charged anion. And it's usually between a metal and a non-metal. The metal is cationic and the non-metal is anionic, has a negative charge. But let's look at organic molecules as a whole. We know that atoms have a skin of electrons called the valence shell of electrons. They are the ones that form bonds, that form the molecules that I've just shown in the board. And those molecules have the same skin and they interact. And you know that the areas of that molecule that are most likely to interact are the functional groups, because there's a charge disparity there. Okay? Now, that skin of electrons also dictates the physical properties, i.e. melting points and boiling points. So if I just give you an example here, if I draw a crystal, it's all nicely ordered like little soldiers in a line, packed on top of each other in 3 dimensions. That's a highly organized crystal. And those crystals are, those molecules in the crystal are held together by intermolecular forces, here indicated by the dotted lines. Does that make sense to you? That holds it together. Now on the x-axis, I'm going to increase the temperature. So here temperature is going up. And at some point, the amount of energy going in, that's being pumped in here in terms of temperature, increasing temperature, is going to overcome these intermolecular forces. Do you see that? So if these are strong, it requires a higher temperature to overcome them. Does that make sense? It requires more energy being pumped in. When those overcome, it all of a sudden absorbs all that energy, they break apart, and now they're swimming around like a liquid. They're not confined to being joined next to each other by intermolecular forces, and they've absorbed all this energy that's represented under this energy curve. So there's increasing temperature. We've gone from a solid to a liquid. Does that make sense? Okay. So melting points and boiling points are determined by the strength of these forces, and the strength of these forces are determined by a couple of factors. And the intermolecular forces, like I showed you, are categorized into 3. In fact, let me just go back there and just give you some abbreviations for those that I'll use. So I'll explain these in a second, but I'm going to use abbreviations from Van der Waals. We'll abbreviate as BDW. Those are also called London dispersion forces, as I said. And then we've got dipole-dipole interactions, which we'll abbreviate as DD. Double D. Anybody a big Ed, Ed and Eddie fan? No? And then, no? It's your generation, surely. Hydrogen bonding, HB. Okay, so that's how we'll abbreviate those. Now, these hydrogen bonds are way stronger than any of these two. So hydrogen bonding significantly impacts boiling points and melting points. So let's look at Van der Waals forces. Here we have a representation here of the electron skin. Maybe I would do my own representation here. If I draw 2 molecules here, they have an electron skin. So think of this skin of electrons as fluid. It's moving over the molecule, flickering over the molecule. And when one molecule approaches the other, and we can choose any one as the approaching molecule, this one, then what's going to happen as it approaches this molecule, it's going to push all the negative charges away from this side of the surface, and it creates a temporary dipole where we have a slight negative charge on this side, and because it's being pushed to this side, it's creating electron deficiency on this side, because this skin is coming along to push that. Does that make sense? So that creates an intermolecular attraction, but it's very fluid. It's a dynamic process. It's very weak, and this, every time a molecule approaches another molecule, it's shifting the skin and creating a temporary dipole, and then it goes back again and interacts. So it's just fluid. It's always moving, and it's weak. Okay, and that usually occurs with molecules with no heteroatoms in them. Okay, so we say these molecules are non-polar, but they're loosely held together by these impermanent dipoles that just fluctuate at a very high rate. And that's van der Waals forces. Those are the weakest of all. Okay. Now, here they've drawn a couple of molecules for you in your slides, but I'm going to represent it a little bit easier for you. This molecule here is pentane here, left. I'll draw it in skeletal form. That's pentane. And I'm going to take that molecule and I'm going to break the bonds apart and I'm going to join it together differently. It's called a constitutional isomer. And I know you were introduced to it in your chapter 1, but I didn't cover it or examine you on it because we'll do it in chapter 4. But if I break those 5 carbon atoms apart and just reconfigure them like this, we get a molecule that's known as neopentane. They both have exactly the same types of number of carbons, and they have the same number of hydrogens. They're exactly the same mass. The only difference is their surface area. So this molecule here has a much greater surface area to interact with other molecules like it. Do you see that? This doesn't. Okay? It's like comparing this shape with a circular shape. When another molecule that has a circular skin comes in contact, they only make a very limited contact. Do you see that? When another molecule like this comes along, it makes a huge amount of contact. Do you see that, the difference? And therefore, this molecule, even though it's got the same mass as this one, this molecule is going to have a higher boiling point than this one, because it can make more contact. The intermolecular forces can be maximized, and it's more to overcome. Does that make sense to you? Yeah? Okay, jolly good. Just look at this molecule. We can look at any type of molecule with a heteroatom. This time, if I was to represent this molecule just in cartoon form, I would draw them both like this. And they have a similar interaction you get with van der Waals, but this time it's not induced by the molecules surrounding it, and it's not fleeting. It doesn't just like fly away and then reform quickly like van der Waals. This has a permanent dipole. This oxygen is more electronegative than the carbon atom, so there's a flow of electrons within that bond that goes in that direction. Do you see that? It forms a permanent dipole. And we can represent it either by drawing a dipole arrow like this, or just by drawing a permanent, negative charge, positive charge here. Does that make sense? So I can represent that here with just a positive and a minus, and a positive and a minus. You can see here that this is called a permanent dipole. It's not induced by the skin of electrons of neighboring atoms. It's there within the molecule. It doesn't have to be created by an outside force. It's inherent to the molecule. And that's a permanent dipole, and so there's a stronger attraction because it's not constantly moving. Do you see that? And that's called a dipole-dipole force because there's a dipole here. There's a dipole. This is called a dipole-dipole interaction. Okay. And that's stronger, mainly because it's permanent within the molecule. It's not made and then lost. So they're the next strongest intermolecular forces. So molecules that have those that have similar mass to one without, these would have the higher melting and boiling points. then the last and strongest of the intermolecular forces is hydrogen bonding. Of course, water is the classic example. So what's the prerequisite for hydrogen bonding? Now, I hate to mention this because I just don't like talking about it, but books always mention it and it's pointless. There are only two appreciable types of hydrogen bonding, and that's within molecules that have OH bonds or NH bonds. But books mention HF, and I know strictly speaking it has hydrogen bonding, but it's of no consequence. It can only hydrogen bond with itself. Okay, that's it. The rest, you can find NH bonds and OH bonds in any type of molecule. Does that make sense? And they can all hydrogen bond with each other. So these are the only ones that have any consequence. Okay, and it's the reason why your DNA is held together as it is. Hydrogen bonding is very strong. Anybody familiar with Gulliver's Travels? Yeah, Jonathan Swift. Where he lands in the land of Lilliputians, these tiny little people, and he's asleep, or he's washed up on the shore or something, I can't remember. And when he wakes up, all these little people have slung ropes over him, but the ropes to him are just like threads, they're easily broken. But there are so many of them, they're so numerous, that it's very strong. It's the same way a normal rope works. A rope is made up of threads. Those threads are wound into like string, and then the string into twine, and then the twine into rope. There are so many little threads together that the rope is very strong. So and that's why DNA is held closely together, but it can be unzipped. They're all individually very weak, so you can unzip it. But together, they can hold it and give it integrity. Does that make sense? So a lot of nature uses hydrogen bonding. So what you need to remember is that if there's an H attached to an N or an oxygen, it hydrogen bonds. And this is a perfect example. Here we have an OH, and here we have an OH. So what's happening here is these electronegative nitrogen oxygens are drawing electrons towards themselves and becoming partially negative. And in order to become partially negative, they have to draw electron density away from whatever they're bonded to. And the easiest electrons to move are hydrogen, so the hydrogen becomes slightly positive. So now it's created this dipole, and it can match up with other molecules that are akin to it. So here's plus, minus, do you see that? And it creates a large network of hydrogen bonds, which are pretty strong. Okay. Now, molecules that have these components together form hydrogen bonds, but one of the components can have no hydrogen, as long as it's got one of those atoms. So I could draw down a ketone here, but as long as one of the other components, like water, in which it dissolves, has hydrogen bonding here, as the hydrogen bonding prerequisite, a minus here and a plus here, it can join together with this. So the red line represents hydrogen bonding. Do you see that? As long as you've got one component that has the prerequisite and has this charge disparity, this is a hydrogen bond, even though it's between two disparate species. Does that make sense? Okay, but one of them has to have this. Okay, one of them has to have an NH or an OH bond. So just to recap here at the bottom, don't know if you can see that. The weakest intermolecular forces are van der Waals. The next stronger is dipole-dipole, and the strongest of all are hydrogen bonding. So I'm going to show you three compounds here. I'm going to show you some examples. There we go. Let's zoom out a little bit.
I have a question about
Yes.
hydrogen bonding.
Yeah.
So you said that as long as one of the components can do the hydrogen bonding, you can do it with it. So with the other compounds, it specifically have to have an O or an A?
That's right. It has to have a heteroatom in it. There are, I mean, you can get very weak hydrogen bonding, but it's insignificant with other atoms. Those are the main ones. They give rise to significant property changes. So look at here. These all have a similar molar mass. All of these. That's how we can only directly compare things when we're talking about intermolecular forces if they have similar molar mass. If something is more massive, it's automatically going to have a higher boiling point or melting point because you've got to put more energy in it to make it move. Think of me and think of a huge big football player on the Louisiana Tech team and one of you trying to push us as hard as you can push me easily. I've got a low boiling point and melting point because I'm less massive. Does that make sense? The football player will require a couple of you to move that guy. Okay, it requires a lot more energy, yes, so higher boiling points and melting. So mass automatically increases boiling points and melting points. That's why when we're looking at intermolecular forces, we have to have things of similar molar mass. And these all have a similar molar mass, but this one only has van der Waals. Yes, do you see that? Now, the next thing you need to learn is that every molecule has the weakest one. So they all have van der Waals. It's just that in this one, it's the only force, and it's dominant. Do you see that? Then we move on to this one, and as well as having van der Waals as dipole-dipole. Yeah? And so does this one have dipole-dipole. But in this one, the dipole-dipole is stronger than van der Waals, so this is the dominant force. Do you see that? But it contains all the ones that are subsidiary to it. But they are not as significant when it comes to the physical properties. And then the last one is hydrogen bonding, which we have here. And that is the dominant force. It far outweighs these two, so it controls the properties of that one. And you can see the change in boiling point here, can you? Yeah? Okay. The next thing I've got to tell you is some other factors, and it's best that I do it just my way rather than the book's way. And I'm going to, I should have written down the actual, I looked up before I came into class the actual boiling points and melting points, but I'll show you the trend here. I'm going to show you 3 compounds, all same molar mass, just like I showed. There's pentane, don't worry about the name, it's got 5 carbons, and it's full complement of hydrogens. If I break it apart and rejoin it and show a constitutional isomer, I can create this type of molecule here. That's called isopentane. And then the last one we've seen before, if I break it apart and join it together on this way, it gives me this molecule. Now, when it comes to boiling points, it's the surface area that matters. The greater the surface area, the more they're held together tightly by their intermolecular force, the higher the boiling point. So we're going to look at boiling points now. This has the highest boiling point because the surface area is the greatest and the interaction is maximized. Yes? I can show you. The next one is this one, and the one with the least surface area joining them together is that one. So this is the highest boiling point. This is the lowest. Okay, and that's BP. Okay, I'm referring to boiling point in all of those cases. Highest, and that's surface area. Okay, some books call it polarizability, which I find misleading, so I don't use it. Then, if we look at the last one here, if I rearrange, I'm going to rearrange these now, and this time we're going to look at melting point, and then melting point is different. This is the highest melting point. And the lowest is this one. Now why is that? This time it's to do with packing efficiency in the crystal. When we're dealing with melting point, we're going from a crystal to a liquid. So the more we can fit into a unit cell, the more mass we've got in a unit area, in a cube area. Does that make sense? I've just told you that the more mass you've got, the more energy you require to separate it. So for every unit cell, we require more energy to separate those. And I'll just represent it as a cartoon here. If I was to draw a unit cell here, we could fit lots of these in together. The next one with these two arms can actually overlay that and go through the arms of this one. They can all fit in really tightly. Do you see that? So there's a lot more mass in that same unit cell. If we do the same unit cell this time with this one, they can all lie right on top of each other. Like that. You can fit a lot more mass in a unit cell there. Do you see that? This one, not so good. Same size unit cell. Depending on how they fit together, it's just not very efficient. Do you see that? Okay. So that explains melting point. So remember that sequence, because I'll ask you about it in your exam. Okay. It's important. Okay, good. What time is it? Do you know? Sorry?
10 minutes left.
10 minutes left, thank you. Next, we'll look at solubility. Like dissolves like. That's not a good diagram. Let's look at this diagram. When we're looking at solubility, let's look at the extremes. We're dealing with organic materials like oils or solvents like acetone or whatever. And then we're dealing with aqueous environments, just water. And just like I explained to you before, if you go to make a vinaigrette or a dressing, whatever you call it, you'll have oil and you'll have vinegar. One's aqueous, one's organic. And they naturally separate. We say they're immiscible. Have you encountered that word before, yeah? Okay. So they're immiscible because they're not alike. One's highly polar and one's non-polar. Things that are polar have heteroatoms in them, oxygens, nitrogens, things like that. Now, if you look at butane, butane is just purely hydrocarbon. There are no heteroatoms in there at all. Do you see that? There are no dipoles that could interact with other dipoles in an aqueous environment or other. So butane is immiscible. They say insoluble. I don't like that word, but anyway, it's immiscible with water, but it's soluble or miscible with carbon tetrachloride. Do you see that? Because carbon tetrachloride is organic. Yes, it's carbon based. Yes?
Yes.
And it's non-polar. You know the carbon tetrachloride is non-polar, yeah? Sure. So we know that a carbon-chlorine bond is polar. Chlorine is electronegative and we have a dipole. But whenever you have a structure that looks like this, it's trigonal planar, and let's say I draw the dipoles of chlorines, they all cancel each other out. Do you see that? So there may be polar bonds, but the molecule as a whole is non-polar. Now that's not trigonal planar, that's the next one that you've got to remember, which is tetrahedral. Tetrahedral is like this. So we've got 4 chlorines attached to a central carbon, but if we apply vector mathematics to that, basically, they all cancel each other out. You see that they're all equally pulling from each other? So even though they have polar bonds, this molecule, it does not have a polarity. Do you see that? So we say that's non-polar, and it would mix with the non-polar butane. Okay, very good. Let's look at acetone. Acetone is polar and organic. It's got a lot of organic part here, so it helps it to solubilize in the non-polar. And it's got some polarity, it's got a dipole-dipole, which we now know from my explanation it can hydrogen bond to it, so that can help it solubilize. Do you see that? But there's a limit to that. Here we have an almost equal proportion of dipole to non-polar. Do you see that? So it can mix in both. If one of them is way outnumbered, then it excludes itself from being soluble, and I'll just show you that in a second. If we look at these two molecules here we have, tell me when I've got 5 minutes to go. You've got 5 minutes to go. Here's ethanol. and here's cholesterol. They both have hydroxyl groups. They're both alcohols. Do you see that? However, ethanol is readily soluble in water, as you know, on the weekends. And that's because the carbon portion is not too huge compared to the polar portion, so it can dissolve in organic material and it can also dissolve in water. However, even though this has a hydroxyl, which makes it soluble in water, which would make it soluble in water, the organic portion is ginormous. So this dominates, and cholesterol can only dissolve in organic solvents. Do you see that? Okay. Now the rule for that is that for every OH, you can't go above 5 carbons for every OH. So here we've got 2 carbons per OH, so that's soluble in water. This is not, because there's a lot of carbons for that one OH. However, if you look at vitamin C, which I believe they've got somewhere in here. I thought they had it in there. Ascorbic acid. You can see we've got 1, 2, 3, 4 OHs, and the total number of carbons is, so it can tolerate 5 times 4 number of carbon groups, and there's way less than that. Do you see that? There's way less than 20, so that's soluble in water. No?
Yeah, farmers, yeah.
Sorry?
Yeah, farmers.
You do? Now, we've got some names which you've encountered in biology. What's the time?
4 minutes left.
4 minutes left. Oh yeah, you're down to that. Tick tock, tick tock. Okay, so Philic means to love. My name Philip is the Greek philos hippos, which means to love horses. Okay, not in that way, but basically that's where my name comes. So anything that involves philic means it loves. So hydrophilic means it loves water. Do you see that? Now, that means it's lipophobic. A phobia is a strong dislike, and lipo is, its origins are for like fat lipids. Okay, so anything that's hydrophilic loves water, hates organic material or oily material, fatty material. And the same goes for this one. Anything that hates water, hydrophobic, is lipophilic. Yes? That makes sense to you? We've got a few more slides. We will start chapter 4 next class, but I'll finish off these slides at the beginning of that class. So we've just got a few things to do. But we've covered a lot of definitions and